What is up, fellas? Welcome back to my channel. This is Tony, aka One Lead One Day. If you're new here, this channel will do one lead code per day, following the pattern of topics or series. Basically, I'm going to be studying with you together on a lead code problem I have never attempted before. Yep, you heard that right. There is no prescripted answer. We're on the same page here. But don't you worry, I got your back and I promise that I will submit at least an average performance code at the end of each video. Here's a little about myself. I come from a non-computer science background, so I'm no better off than most, if not all of you, in terms of coding knowledge, but that is okay. It is all about learning on the go. You can think of this video as a first-person gameplay of cracking leak codes. And who doesn't like first-person gameplays, right? So without further ado, let's start today's coding problem. We continue on series 1, everything about dynamic programming, and today's problem is 198 house robber. Let's take a look. All right, house robber. Sounds in, sounds interesting. You are a professional robber. Oh, great. Planning to rob houses, better, along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected and it will automatically contact the police if two adjacent houses were broken into on the same night. Okay, so timing matters. You want to be cautious. Don't want to rob two adjacent houses in one night. Given an integer array, nums representing the amount of money of each house, return the maximum amount of money you can rob tonight. Okay, just one night without alerting the police. Cool, cool. So this is about robbing a house, robbing houses, and we can. Yeah. So literally, we don't want to rob adjacent houses because if you do that, it will contact the police. Um, right. So let's take an example. If nums equals to 1, 2, 3, 1, that is like there's four houses. First one has maybe $1, let's say, or 1 grand in it, and the second one has 2 grands, third one has 3 grands, and the fourth one has 1 grand. And then you can pick the houses that with the most money and rob them. But since you don't want to rob adjacent houses, the maximum number of houses you can rob is two. So you better take 1 and 3, and that'll give you 4. But this is like a combination problem, right? Like it doesn't matter about the sequence. Well, yeah, I mean you can rob number 3 and then go on to rob number 1 as well. So this is not a permutation problem. It's like a combination problem. Okay, all right. Example 2. Now I have 5 houses, and now let's see. We can rob maximum 3 houses, 2, 9, 1, right? Or we can rob 2 houses, let's 7, 3. So obviously we're going to take the 2, 9, 1 combination because it's going to give us 12 grands. Uh-huh, right. So there are some constraints of the problem. So the number of houses on that street is between 1 and 100. And the amount of money, wow, it could be 0, that's a poor house, or 400, that's a lot of money in the one house. Okay, so we got the problem. Um, how are we gonna crack it? Well, this again uh, sounds like a something like you can use sampling, but since we're working on dynamic programming series, we will always try to solve this using dynamic programming. And one of the, I guess, criteria or one of the characteristic uh, you should find um, to see if this can use dynamic programming is that if the problem can be broken down into smaller sub-problems. And by solving those sub-problems, can you um, come back and using a kind of a lookup mechanism to solve the original larger problem? And I think in a way, yes, because if, for example, there are 10 houses in that block or in that on that street, you can break them down into, for example, um, 5 houses in the front and then 5 houses in the rear, and then try to solve them. Or if there are 10 houses, you can break them down into um, the first house and then the remaining 9 houses, or the first 2 houses and the remaining 8 houses. Uh, and for the remaining 9 or 8 houses, we can again break them down into sub-problems of 8 houses and 7 houses. And I think that this last suggestion that I made is a good intuition or a good way to do it in dynamic programming. So let's see if we can actually make that work. Okay, so uh, let's try to draw a few houses here, and let's see if we can come up with a heuristic to do it in dynamic programming. There we go. So let's say we have 1, 2, 3, 4, 5, 6 different houses on a street. And so we want to break them down into sub-problems. And and one thing we need to notice is that we definitely want to take either one of these two, because whatever you take down the street, um, taking uh, taking number one is definitely free, and depending on whether you take number three or not, you can choose to take number two as well. So definitely take one, right? Like so, um, definitely take one of them, one of these, rob one of these, right? Um, and then we're gonna move on to the sub problem of this. So this look like we can yeah we can break down this problem into two sub problems. Um, let's say this is problem 6, right? Problem 6, because it has 6 houses. Um, it could be equivalent to, because we're trying to maximize, right? Like because we're trying to, maximize, m- maximize, maximize reward, right? Maximize reward. So we could think of this as um, taking one action, right? Because in DP it's all about, action, reward, and then, the maximum remaining reward, things like that. So if the first action is to either take either go with number one or go with number two, then we can calculate, the remaining maximum reward. Um, right. So this will become, let's say, um, Yeah, we can use R because right, like R6 is gonna be like the maximum reward, right? Um, Maximum reward of that. Um, we can say it's equal to R reward of taking one. Mm, yep. So let's see. One is that like a state? Yeah, it's probably like a state. So, mm, reward one. Okay, we're gonna use the number in the parentheses to indicate what? To indicate um the the beginning and the end of our array. So we're gonna if we say 1 1, for example, if we say 1 1, that means we start from 1 and um end at 1. Okay. And if we say 1 6, that means we start from 1 and end at 6. So yeah, that's what we wanted to try to do. So let's just do that. All right, let's see. 1 6, that means the total reward from the first house up until the sixth house. This will be similar. This will be equivalent to 1 1, which is only the first house, and then plus the reward of 2 to 6. Right? Well, actually, let's not use R because this is directly taking one. So um, let's say we're gonna use the little r, um, yeah, to represent, a one-time robbing, a one-time robbing reward, like the arc cost in dynamic programming. Because in the end, uh, we want to summarize a relationship that is like the Bellman's principle of optimality. Now, but this is only part of the story, right? Because, like we said, between 1 and 2, you can either take 1 or take 2. So this is just one of the possibilities. We also need to plus the other one possibility, which is to take the reward of the second house. Uh, and well, if you take the second house, definitely you're not going to take the first house, and definitely you're not going to take the third house because those are adjacent. So you're only going to take um, some house or houses um, from 4, 5, and 6. So we will take our 4 to 6. All right, so does that cover all the possibilities for the first step? Um, yeah, I think so. Wait, hold on. This is wrong. This is like 3 to 6 because we're not definitely not going to take 2 if we already took 1. So R1 plus R3 to 6 plus R2 plus R4 to 6, and that does cover the first step, right? Yes. So you see, this is already like a recursive relationship. Um, but what about, the next few steps? Can we propagate this down? Right. Let's try to express R3 6 and R4 6 in the next step. Right. So this is like step 1 and step 2. We can try to see if we can express R3 to 6. And you see, if we just write it down, 3, 4, 5, 6. Now again, we're faced with two different choices looking at the first two houses. Um, Again, we can take one of we can rob one of them, right? Rob one of them. And then so this is equivalent to, again, either rob house number three and then find out the maximum reward um, of robbing houses between 5 and 6, or we rob house number 4, uh, and then we can rob, well, then we can only rob number 6. But then still, just for, um, you know, um, the consistency of the form, we're going to say our 6 to 6. This is like the last step, or like the last house we can ever rob. So we can stop here on this branch. Um, well, there's still another value to calculate. That is R4, 6. But because now we only have 4, 5, and 6, um, of course we can still rob one of them. Uh, but then we're left with only one house to rob or not to rob. So we're gonna do R4 if we rob the first one, and then we're gonna have a remaining maximum reward between 6 and 6 itself. And if we rob, let's say, house number 5, then there's no more houses to rob. So that's like at the end of it, right? So, and then if we calculate all these things, like, yeah, this is the original value we want to work out. In order to determine that, we can perform this R36, R46, and then it would involve a calculation of R56 and R66. Um, then we'll definitely get to the end of it, and then in between we also calculated a few individual robbing values, and these can be just a lookup at the original value array, which is the nums array. We can look up 1, 2, 3, 4, 5 different values. And well, hold on a second. We still need to calculate R56 and R66. So let's just write them down. What is R56? Well, because now we only have 5 and 6, we definitely just because there's only two in them. Oh, I just realized I made a mistake. Instead of plus, all these things, they are they're actually max, right? So it's definitely not like this. It should be uh, a maximum between those two. Yeah, again, this is like, be super careful, guys. Don't make a same mistake like I just did right here. But I'm lucky to have found it out immediately. You want to maximize between this value and this value instead of adding them up. That's not how dynamic programming principle works. So dynamic programming principle, there's always like a max or minimum function between different choices on the same step. So here, similarly, we're gonna do a max function of these two values, right? And same here, same here. So I made a mistake or mistakes by thinking that we should use addition here, but it's actually not. It's actually the maximum function we need to use. So this is a great lesson. hopefully, when we move on to do more dynamic programming problems, we'll not make the same mistake again. All right, so R5 and 6, it's simply comparing the maximum between R5 and R6. So for R, for R66, because it's just one value, we just say R6. So there are some, I guess, exceptions here. First exception is that when, the first input is actually the same as the second input, you just directly return the single value of robbing one house. And the other exception is when, the first input and second input are like next to each other, then you just do a max comparison between the single values of robbing two single houses. Other than that, when the distance between the first input and the second input is greater than one, then you can start this kind of comparison. Yes, this kind of comparison. Uh, and of course, the second input is always, if you see here, the second input is always 6. It's never it's never something else, right? Like it's always 6. So actually we can save some yeah, save some code and um yeah, you see the second input is always 6. So we're gonna have a change of notation, right? So notation change. Um, so RK of, uh, 6, now we're gonna turn into RK because um, because the second input is always gonna be 6, so we don't really worry about it. Uh, so yeah, we should do that. And shall we just erase everything and do it that way? Let's do that actually. Just for clarity, we're gonna remove that. All right. Yes. And then here as well, we just remove that extra 6. That doesn't really mean anything. Here we go. Here we go. We just remove them for clarity. Yes, and here and here and here as well. All right. I think we are ready to implement this algorithm. Uh, let's now go back to the problem itself. Uh, copy the copy the title and the description, and again we're gonna use mm, Python. Again we're gonna use Jupyter Lab to as our IDE to prototype our algorithm. So we build a new one. We rename it. Uh, Today's problem is 198, and then here is our title, and then we're gonna also copy the description in here, and then we also want to have some examples in here. All right, right, markdown, and we want to copy the solution structure template and start writing our solutions. Okay, so the function name is Rob, which is pretty short uh, and good. Now, since we're going to use dynamic programming, we need to have a storage unit that computes that stores our computed value of the R's, or like the rewards, right? So we're gonna we're gonna be consistent with our use of symbol here. We're gonna use R, right? And we're gonna use dictionary because I am still believing that dictionary is more efficient for lookup than lists. And lists, it will uh, because when we use lists to look up, we will actually walk from the first element in the list all the way up to the index we indicate. So it's gonna take a walk, take quite some time. So we're just gonna use dictionary to actually do the lookup. Uh, Dictionary to store the uh, reward, the max reward uh, of robbing. Like it'll be, for example, and we're gonna use again the the string version of integer to um, write to string version of integer to uh, as keys, and then uh, for example, uh, wait. So one means all the from one down to the end of it, right? Like the value of robbing houses, um, you know, from mm, k to n, right? So number one is like all the houses. In this example here, it's gonna be four. Uh, and then if it's two, that means robbing houses from two to four. That would be maximum three, right? So three, and then if it is, in this case, three, so that's three and four. Then the value is of course three, because we can just rob house number three. And then number four, in this case, the robbing value is just one. Yeah, example that for example one. Right. How? Okay, that's good. And how are we gonna use it? Well, for dynamic programming, we knew from yesterday's exercise that we can basically use a for loop build build up all the values uh, in this max reward uh, max reward variable, or aka cost to go or reward to go uh, value. So, and we're gonna just basically copy this relationship here. But I think right now we do need to kind of like generalize this expression into some kind of expression, right? Like an expression where the numbers are no longer um, yeah, the values are no longer like um, actual actual digits, actual integers, but like k and k plus one, things like that, right? So let's try it. For example, we have n houses, and then we look at the value k less or equal to n. Uh, so what does rk equal to? So rk, in terms of houses, it'll be looking at um, like k plus 1, k plus 1 all the way to n. So those are like the houses. And then of course we're gonna take a look at the first two, whether to rob one of them. Um, and then we're gonna separate our expression from there. So RK, this is gonna be um, a max between uh, R, you know, small r of k, just robbing the kth house, um, plus, capital R of, uh, because we're not robbing k plus 1, we definitely need to start from k plus 2. And then the other one is if we skip k and we just rob k plus 1, that leave us with the remaining houses starting from k plus 3. Right? Right. So this is the iterative expression for that. And we need to be careful because maybe this k, when k grows, uh, these things will exceed like the total number of n, right? Uh, well, it could be, but this is really not our direction of calculation. For us, we actually calculate it backwards, right? Like um, from k6 back to k equal to 6 back to k equal to 1. Uh, that's like the bottom up approach. We're gonna stick to that for now. So we're actually going mm, from k equal to 6, calculate that first, uh, and then we're gonna calculate k equal to 5, k equal to 4, k equal to 3, k equal to 2, all the way to k equal to 1, and that's the answer we want. Right, so for k equal to 6, we just use this expression here. And for k equal to 5, we're gonna stick with this. And these two are exceptions because, uh, right, because uh, this is the last one, and we can just build it by just look up the last house value. For the second to last, it's a simple comparison, so we can just hard code this as well. Uh, that is if we do have, more than one houses, uh, right? And then we can, yeah, then we can move on to R4, which is again a little bit special because it doesn't have the full expression here. Right, and then when we move on to R3, this becomes the generalized expression. So I guess uh, the last three elements are kind of like special. So these three are kind of special. And moving on from the fourth one onwards, expressions are going to be all the same, and we're going to use the same recursive relationship for these ones, more general ones. For the first three, we're going to use like custom expression for each of them. But also, we want to make sure that we cover the cases when there's only like one house, two house, or three house cases, because in those cases we don't need the general expression anymore. Uh, so we're gonna separate those as well using, I guess, if conditions. Right. We can use if conditions to determine if we do need to move on, if we do need to move on to yeah, to further cases. So um I guess, right, I guess we can say like if n is uh n is greater or equal to 1, you do that. well, you definitely do that. So there's no if condition needed here. But, for the second to last, this is when if um, n is uh, n is greater or equal to 2, you do that. And if n is greater or equal to 3, you do that. Um, yeah, you do that. And what about R3? Because if it's greater or equal to 2, you also want to do the more general thing. Um, right, so this is when if n is greater or equal to 4, then you're going to do the more general computations and all the way down to the first one. So that's how we're going to implement our algorithm. We're going to build a few if conditions to signify the necessity of subsequent computation, and then we're going to work our way, all the way to R1 eventually. Right, so let's do that. So the first case is uh, calculate the last reward, last house. Calculate, Rn, Rn, right? But it's actually with a string, so we're gonna use that. Uh, yes, and here we go. Nums, right? So we definitely need to find out a number in here, like num length of that nums, right? So um, the first one we don't need an if condition, so we're just gonna say R of uh, string conversion of the the largest number in the an array. This is going to be a direct lookup of nums, which one, um, the last element, right? But because nums starts with zero, the index in nums in a list starts with 0, we actually do n minus 1 to look up the last element in it. Okay, so next calculate r uh, n minus 1, but if n is greater or equal to 2. So if uh, n is greater or equal to 2, we're gonna do our str n minus 1 equals to, let's look it up. So the second to last is going to be a maximum between the last two house values, right? Max between um, nums m minus 2 and nums m minus 1, right? And then we calculate r n minus 2 if n is greater or equal to 3, right? If n is greater or equal to 3, and we're going to again use a special expression, which is this one here. So it'll be like this, and right. So this will be n minus 2 uh, max. Now this becomes uh, the first element is going to be nums n minus 2 plus looking up uh, the string value of m minus 4, I believe. Yeah, well, no, actually, no. This is like the last one. This is literally the last one. So, um, right. So it'll be this. And then nums n minus 1, which is our, no, this is like the non-capital R. So, yeah, yes, that's nums. Right, that makes sense. So, that is that. And we're going to say calculate the remaining r's, r values if n is greater or equal to 4. So if n is greater or equal to 4, we're going to do the for loop. And now the for loop, it starts at, let's use k, right? A range of what? The first value we're going to use for k is n minus 3. And of course, because we're going backwards, we're reducing our um, number by 1 each time. And are we going back to 1? Yes, so we're going to use 0 here as our last input parameter. And for the k here, now we can write the general expression that we worked out in here. Exactly this one thing here. So rk, capital RK plus 2, RK plus 1, capital RK plus 3. And it's a max between them. So we got it. It's going to be str of k, right, equals to max between two values. And the first one is nums k plus 1 plus r of k plus 3, right? Let's just look it up. Yeah, plus, well, it's it's k and k plus 2. Okay. All right, so this actually is the second one, but that is okay. The first one would be just k and k plus 2. And I think here we got it, and that's everything. So once we've finished this if slash for loop structure, we'll have com completed um, the process of filling up the dictionary R, which means the maximum reward for the for the yeah for all the houses on that street. And we're just gonna return what? Return um, R of 1. Yeah, I think that's about it. And it's quite elegant, I guess, this time. And then hopefully we can just do a one pass. So let's try to, get some test cases there. Uh, we're gonna just steal one of those test case syntax here, and for the first input, of course, we're gonna have 1, 2, 3, 1, 2, 3, 1, right? And then we're expecting the answer to be 4, right? So we're gonna do srob of 1, 2, 3, 1 and see if it's 4. And we can use the second example from Leetcode and then the answer as well. So input here, and what are we expecting? We're expecting 12, right? So we have those two things to expect. Okay, let's just do two test cases and then see what we got. We got some error. Interesting. Name R is not defined. And why is that? Well, I think we ran into this before. For some reason, uh, the dictionary was not uh, defined. Well, you know what? Um, Actually, we don't have to put it, as right. We should use like self. But you know what? We don't actually need to place it as a class property. We can just use R here by, initializing it inside the function because we only use it in this function. So there's no need, I guess, to place it outside as a class property. We don't have a second function to share it. So let's just do that, right, and see if it works. Still, uh, okay, range arg3 must not be 0. Oh, why is that? Why is that? I mean, that is pretty weird, huh? Because we want it to go down to 1. So why this one cannot be 0? I don't know. All right, let's try -1, but probably this is gonna perform some overflows. Okay, list object is not callable. Right, there's a syntax error here. No round brackets for list indexing. Okay, so let's try again. Well, it's a little larger than that. I guess because we iterated once more because we added this -1 here. So k actually went down to 0. So, and we didn't want that to happen. Well, I guess then we're gonna just have to readjust the indexing here. Let's just, yeah, readjust the indexing and go from 1, start the index at 0, okay? So if that's what we're gonna do, I'm gonna change this to rn -1, and right, and it's gonna be like that, and it's nums n -1, so that's actually a good match. Rn, hmm, right. Yeah, because there's n houses. There are n, well, there are n houses, right, in that element. Yes. So you're gonna use n -1 as the index of the last one. Makes sense. So we're gonna just change this to n -2, and then this will become if n is greater or equal to 2. Yes, yeah, okay. If n is greater or equal to 2, we're gonna do rn -2. This will become, uh, do we change this? Do we change this here? Well, Yeah, if we're using this one here, you're right, the second one, let's take a look at our expression here. Second to last, we're gonna do this one here. It's max R5 and R6. Yes. So if it's an index starting at 0, um, we'll be comparing. So this will become R4, and we'll be comparing R4 and R5 because there's no more R6, right? Right, right. So, all right, let's just yeah. So this is correct. Calculate n minus 2 if n greater or equal to 3. Right, 3. Is that right? N minus 3. So it'll be the third to last. Mm, yeah, and it'll be this one here. We'll be comparing R4 plus capital R6 and with R5. Uh, yeah, so if we use indexing starting from 0, this will become R3, and this will become small r3, and this will be R5, and this will be R4. So it's 3 here, it's 3 here, 5 here, 4 here. Going back, so this is 3, excuse me, this is 3, and this will be 3 as well, and this will be 5, and this will be 4, right? So it'll be like that. Um, Calculate the remaining value if n greater or equal to 4. Right, so now we're gonna start, instead of starting from R3, now the 3 here becomes 2. So we're gonna start this from number 2, right? So minus 4, all the way to 0 this time. And this shall be correct. And for example, um, when we use 3 here, so 3 equals to m minus, uh, yeah, so if we use indexing starting from, um, starting from 0, this will become 2, right? Just alternatively, and this will be 2, 3, 4, and 5 instead. Uh, and then this will become 2, and this will become 4, and this will become 3, and this will become 5. And okay, so does it change the general expression? So this will become, let's see, k, yeah. And is this still k plus 2? Yeah, it is still k plus 2. Is this still k plus 1? Yes, it is still k plus 1. Is this k plus 3? It is still k plus 3. Okay, so we just confirmed ourselves that the general expression doesn't change. That's like the same whether you're using 0-based indexing or 1-based indexing. It doesn't matter. So this expression still holds. We're gonna just use that. And now instead of returning R1, we're returning R0. Right. Let's see if it works. Yep. Everything is now expected, as expected. Great, great, great. And now let's just try to send this solution out to Leetcode and see if it passes our test cases. It does. What about more? Yeah, the second one it passes as well. Let's submit the code and see how good it's performing. Well, yeah, but you see, it's not fast. It's using a lot of memory. So this is like actually a poor submission. Um, well, runtime this time it's a little faster, but still we're using a lot of memory usage. So yeah, this time it's actually, faster than most of them, but still we use a lot of memory. Let's try it again. Whoa, wow, hey, how about that? 75% faster than most of them and 97% faster than, you know, than others. So I guess this is like an average code, um, overall, but definitely there's something better out there in the solutions. So we can take a look at the solution and maybe inspire ourselves a little bit to make some small improvements if possible. All right, so let's go into the solutions and take a look at that. Hey, nice visuals. Uh, professional robber in for a treat, and quick buck, jackpot, last house, right? And uh, yeah, so this is a second way of doing it. If you just take those two houses, you only got 250. Series of choices, subset of houses from the original list. We will make these choices in a way that overall profit is maximized. Um, so there's no greedy way of deciding if the robber should rob a house or not. No greedy way because yeah, it's not the full picture. You need to have the full picture to make good decisions. If you just take a look at one house, even if it's like $1 million, 2 million bucks, it doesn't matter. Maybe the next house is like maybe 3 million bucks, right? So, um, so greedy is not good. We need a global strategy. Uh, you could argue, right? Still local. We need a global strategy. Recursion with memorization. Okay. It's a pretty long description, but it comes down to a tree. Uh, and then recursion with memorization. So you're gonna memorize the values of robbing subsequent houses, overlapping subproblems in the recursion tree. Makes sense. And you have these solutions. Dynamic programming. Yep. Dynamic programming is the one that we want to look at. And complexity analysis, ON and ON. Just out of curiosity, I want to see how fast is this solution compared to ours. Right, let's just submit and see. The runtime really sucks actually this for this one. Let's just try it again. The memory usage is pretty good, but okay, so it beats like Python 3 users, but still, the runtime is more actually compared to mine using just Python. So I'm not saying that mine is better than theirs because it's two different coding platforms. Uh, but this solution does seem to be not so fast um, than others. It's not a very good solution, so to speak. Uh, but hey, are we going to compare our dynamic programming solution with the solutions? Yeah, sure, why not? So let's just read it and see whether there's something new that we didn't know. Here, the idea here is the same as before, except that instead of following the recursive approach, we will be sticking with the tabular approach. The recursive approach may run into trouble The recursive approach may run into trouble when the recursion stack grows too large. It may also run into trouble because for each recursive call, the compiler must do additional work to maintain the call stack, which results in unwanted overhead. The dynamic programming approach is simply a tabular formulation of the ideas presented above. The cache we had before will still exist in this approach, but instead of calling it a cache, we'll refer to it as our dynamic programming table. Every DP solution has a table that we populate starting with the base case or the simplest case for which we already know the answer. For example, for our problem, we know that in the absence of houses, the robber will make zero profit. Similarly, if there is just one house left to rob, the robber will rob that house, and that will be the maximum profit. We start by populating the dynamic programming table with these essential values and then build the table in a bottom-up fashion, which is essential essence of the solution. Let's look at the algorithm to formalize this idea. All right, sounds all good to me. Nothing new. Algorithm. One, we define a table which we will use to store the results of our subproblems. Right, that's your uh, you know, reward to go table. Let's call this table max robbed amount. When max robbed amount I is the same value that would be returned by recursive I in the previous solution. Okay, you're talking about something in the previous solution, which I don't really care right now. Two, we set max rob amount n to 0 since this means the robber doesn't have any houses left to rob. That's zero profit. Additionally, we set max robbed amount n minus 1 to nums n minus 1 because in this case there's only one house to rob, which is the last house. Robbing it will yield the maximum profit. That's right. So are you suggesting you are using a list to store them? Okay. We iterate from n minus 2 down to 0 and we set max robbed amount I equal to max robbed amount I plus 1, max robbed amount I plus 2 plus nums I. So this is the iteration that you discovered for your problem, right? Yeah, okay, so there's a max, of course, and there's a max robbed amount I plus 1. So the next uh, maximum reward to go, it equals a max between that and max robbed amount I plus 2 plus nums I. So this is like skipping the house labeled I plus 1 and then go directly and then rob this current house, right? Rob this current house and go to and then jump one house. Right, so this is a complete decomposition. It's a good recursion as well. So it's a little bit different from our recursion in that I think the way it is broken down, this expression looks simpler because uh, it doesn't have like an arc cost attached to this choice here. Um, Whereas for us, we take robbing I plus one as an arc cost, and we also then add that arc cost um, to the reward to go function at I plus 3. So that's where you will see those things. Uh, well, those things meaning we have, you know, k plus 1 and k plus 3 here. For you, you're just like I plus 1. And I think it is okay. Essentially, it's the same, but you're just saying that, you're only considering you're only considering this arc cost plus uh, the cost to go here. But for this one, you're just reading a stored value. That's fine. It's like you're taking half a step, where for me here, I'm taking a full step. Um, right? Is that right? Yeah, because we're looking up the value of k from the stored value of like k plus 2 and k plus 3, and you're just looking up value of I from the value of I plus 1 and I plus 2. Yeah, for me, the recursion actually goes down further. And actually, you know what? I think he might be right. I can probably I can probably reduce, my expression to a simpler form if I follow his way of recursing um, through the different steps. So yeah, so I think definitely that is something that I can do to improve our code. Yes. So we're gonna actually go ahead and do that, right? So let's do this. Let's say an improved version, a simplified expression for the same code above. Therefore, um, we don't need to, I guess, jump too many times. Um, maybe we don't need to do the m greater or equal to 4 thing. We just need to stop here. Um, right. I'm thinking maybe we can just promote this up here. We can promote this up here. And we don't need to do this anymore. So yeah, we don't need this anymore. So here we're gonna start from n minus 3 down to 0. But for the k expression, we can do that and that, right? Is that right? Because I think that's the expression we saw here. I plus 1 and then I plus 2 plus I. Um, right, this is like, robbing this house, this current house, right? Rob this current house and then jump to k plus 2. So that is like robbing the current house and jump to k plus 2 or I plus 2. Yep. And comparing it with the maximum reward starting from I plus 1 or k plus 1. So that is in spirit the same here. So right, um, let's try that. This is like the same expression. It's just a little bit simplified in terms of the idea. Yep. So I think we got a better version of the code. It's more compact, right? It's more compact, less lines. Oh, and why not? If we can use less lines, we may actually have a better performance now. Right. Here we go, run code, passed, and run test cases, also passed. So let's submit this and see if it's better. 35 milliseconds. It's like before. Let's just do it one more time. 26 milliseconds. So in terms of performance, it's similar to what we had. It's just that, in terms of writing, this becomes this becomes more simplified. So actually, I like that better than our previous solution, thanks to looking at the solution of this. So great, we had an improvement. All right, let's just finish reading this dynamic program from the solution, see if we have more takeaways. We were on item number 3, so you have this recursive relationship. That's good. And then note that this is the same as the recursive formulation in the previous solution. Okay, I don't care about previous solution. The only difference is that we have already calculated the solution. So we solve problems and we are simply reusing the solutions in one time and calculating the solution to the main problem. Right, we return the value. Right, so now you have this function here, uh, empty case, right? Oh, you have a list comprehension. That's smart. And then base case initialization, right? You're using a tuple to tuple kind of like initialization, which is great. Uh, DP table calculations. Okay, you have the for loop. It's exactly similar to mine. And then you have that expression, which is now exactly similar to mine, but it's only that, you're using list and I'm using dictionary, so maybe I'll be more efficient than you, that kind of deal. Yep. So yeah, that's actually dynamic programming solution. Nice. Oh, there's approach number three. So by the way, we just finished reading this solution approach number two, and it's basically the same as ours, just that the solution used lists where we use dictionary, and solution used Python 3, we used Python. So time complexity O(n), since we have a loop from n minus 2 to 0, yeah, it's in a linear order, right? Uh, you have a loop, so you need to use that loop to perform, n times. Space complexity, so the table, because the table stores up to n different values, right? So that's O(n) and O(n). Approach 3, optimize dynamic programming. What can you do better? Let's just jump down to see if the oh, okay, wow, the space complexity dropped quite a bit. Let's take a look of what this is. Maybe we can learn from it and optimize our code. This is the exact same solution as the previous one, with the exception that we will be optimizing the space complexity here. Let's look at the recursive relationship again to see where we can reduce the amount of space used. Right, so this is the recursive relationship that we agreed on. To calculate the current value, we just need to rely on the next two recursive value calls. Next two, yeah. Oh, you're right. We can throw away. We can throw away, the calculation that we've built up all the way through, you know, uh, our n minus one, up, up to, uh, you know, if we just want to calculate rk, we just need rk plus 2 and rk plus 1. That's it. And we can throw away the previous calculated values, right? So we can just build a cache that only stores two values, right? And we can just, rotate that and get better. I agree. I love that intuition. And without looking further into the solution, I think uh, we're going to move on to a better complexity solution. So yeah, uh, optimizing space complexity, reducing dictionary to just two values, right? Because we only need two. And instead of using dictionary, I mean, actually, you can still use dictionary. I mean, there's no to store the two values of k plus 1 and k plus 2. Right. We are actually just storing these two values. And yeah, let's just say that. We're going to explicitly state that, right? So something, uh, right, let's say k plus 1 equals to like that, and k plus 2 equals to like that. Right, something like that. All right, so calculate, um, that. Okay. Mm, k plus 1, k plus 2. So how are we going to do this? How are we going to do this? Uh, but of course, at each step, we're going to update what k plus 1 means and what k plus 2 means, right? So we initialize uh, rn minus 1, right? We store it, but this time now, eh, instead of saying that, we just say uh, k plus 2, because this is like the last one, right? And then um, what do we do? Um, right. Um, right. Eventually, what are we returning? We are returning. Um, mm, mm, mm. Let's see. Well, yeah, I got a little bit confused of what should we do about this. Uh, right. So shall we do k plus 1 here? Right. And okay. Um, and we can iterate this, right? So yeah, we can iterate this and we can say as we move on, our because yeah, it's gonna be literally just a string now. And this is like what k plus 1. And right, we're just gonna say the new. Right, after we do this, we need to actually, update those two things. Uh, yeah, so this is actually gonna be yeah RK, but you know it'll be RK. Yeah, it's true. Um, but yeah, so we're gonna rotate those things. Now our new RK plus 2 is gonna be RK plus 1, and then the new RK plus 1 will become R of K, right? So this is like the update. And you're gonna rotate and rotate and rotate until you get to RK, right? Yeah, I think I got the bulk of it. Just that we need to probably do a few things here. Right. So yeah, what if like for the special cases, what if n is just one? Uh, if n is just one, we're gonna definitely just return this, right? And your our RK is just gonna be uh, RK plus 2. And what if our yeah, what if our n is exactly just equal to 2? Then yeah, it'll be this, right? And Yeah, let's try it. I mean, I can't really figure out everything in one step, so let's just try it. It actually worked. Okay. All right. I think I just uh got myself through this maybe by chance. Yeah, let's try another one. It actually works. Let's submit. Bingo. There we go. Yeah, so now we actually implemented this uh, improved version of code, and it beats the majority of the solutions there. Now you see runtime is really good. Memory wise, it's really good as well. Let's try it again. Yep, beats 54, 41%. Let's just try it one more. Yeah, memory wise, 67% better. So there we go. Um, Great. I think that wraps up our learning from the solutions. And today we did a pretty good job. So here is our summary, right? Today we looked at the house robber problem, and then like before, we realized that this problem can be solved using dynamic programming. So we went ahead and derived our own recursive dynamic programming relationship here, which is here in red. Um, it's a little bit old school. It's based on this, arc cost and cost to go uh, uh, notion, and we're basically maximizing all the possible combinations of arc cost and cost to go for one step, and then we're using this for recursion. And we also use the bottom-up approach, and then we just start from the last house to rob, and then backwards, and then we say we look at what is our reward if we start from the second to last house, and all the way to third to last house, and then fourth to last house, uh, and then moving on. And we realized that the first case, the second case, and possibly the third case are special cases because the expression for the for the maximum reward is a little bit different from the general expression because we're just towards the end of it, right? And then starting from the fourth uh, to last, we can use an expression that is general, and we can just use a for loop to loop over them to until we find R1, which is what is the maximum value if we start from the first house onward to rob. Uh, so this generally worked, and the space complexity and the time complexity were both O(n) in this solution. Uh, and I think we struggled a little bit with the choice between zero indexing and one indexing. So we actually did switch from one indexing to zero indexing in our final in our version one code submission. But then um, after looking at the solutions, I realized that this expression can be simplified. So I'm just going to write down actually the simplified equation just to as a recap, right? So the simplified expression, as I'm writing here, it's going to be, yeah, the simplified solution is Rk equals to max of uh, just Rk plus 1 and small r k plus capital R k plus 2. So this is just a simpler expression than our version 1. Uh, it does the job as well. And in this new expression, we didn't need to treat the third to last case as a special case. We actually will have um, all these cases, 4, 3, 2, 1, as general cases. And we only have two special cases to deal with at the beginning. So this is like a better one compared to this. Um, so next time when I start with Bellman principle expression, I'll consider this one first. All right. Uh, then we looked at solution and found out that there's actually an optimization of dynamic programming that you can that we can exploit to reduce the space complexity from ON down to O1. So how was that possible? Well, um, because we only have, two choices at each step, whether, to skip this current house or to, actually take the current house. Uh, because of that, we only need to remember um, the, uh, the maximum cost, the maximum reward to go for the next two houses, right? Down the road. We don't need to look further because we only have two choices. We only need to look up, two maximum reward to go. So we can exploit that actually, and instead of like using a dictionary to build up, you know, all the maximum reward to go from R6, R5 all the way down to R1, we can just you know store two values, and we're gonna call one of them R uh, K plus one, and the other one R K plus two. And our definition of K can just roll as we go. So instead of storing like, a lot of values, we can just store two values. And that is the inspiration, and we actually implemented that fairly quickly, and it did result in a more efficient space usage, memory usage. So yeah, that is the summary for today's problem. Uh, Again, it went pretty well. Here, let's take a look at our different versions of code here. We're gonna just annotate this with like version one. Version one, a little clumsy, recursive DP expression, right? That is our version number one, and this is our version number two. A more a simplified uh, recursive DP relation. And then we have finally our version 3, which is an optimized space complexity, reducing, yeah, the dictionary size just down to just two. Yeah, and because now the dictionary has only two, we actually can, instead of using dictionaries, we can just use list. But yeah, we can stick with dictionary. And the good thing about dictionary is that we can have actually a string key, and it would be so easier to read actually using dictionaries because you can define your key as whatever suits you or you find easy to read. And so that is that. Uh, the code looks great, and our scores are really good as well. And that summarizes today's coding problem. Again, thank you all for sticking along with me. Hopefully you learned something useful in the process, and I'll see you in our next video. Peace.